Artificial intelligence is currently writing code, passing medical exams, and generating video on command. While the speed of progress appears limitless, one of the founding fathers of the field suggests this current trajectory has a built-in ceiling. Richard Sutton helped invent the algorithms used in modern artificial intelligence and authored the primary textbook on reinforcement learning. As Silicon Valley invests billions into large language models, Sutton takes a different view of where the future of the mind actually lies. Large language models function as sophisticated next token predictors. Given a prompt, the system calculates the mathematical probability of the next word based on the statistical patterns found in human training data. These results mimic human conversation. However, the system lacks an internal model of the physical world. It operates without a definition of ground truth, relying instead on what is statistically likely to follow the previous word. Without a specific goal to achieve in a physical environment, it has no way to verify its own logic. This architecture also faces a data limit. Training these models requires massive data sets, and researchers are now reaching the end of high-quality human text available on the open internet. A machine designed to mirror what humans have already said is constrained by the boundaries of its training set. It can reflect our existing knowledge, but it cannot independently investigate reality or uncover principles we haven't already documented. Sutton explored this problem in a 2019 essay titled The Bitter Lesson, which outlines a repeating cycle in the history of AI research. For 70 years, researchers attempted to manually program human knowledge, logic, and rules directly into computers. These projects required immense labor to define how a machine should interpret a specific image or structure a logical argument. Historically, these hand-coded systems are eventually outperformed by simple methods that rely on scalable search and raw computation to find their own solutions. Current language models use significant compute power, but the underlying philosophy remains the same. We are still attempting to reach intelligence by feeding the machine what we already know. Breaking this cycle requires a shift in focus. Instead of telling the machine about our world, researchers must build systems capable of discovering the world through their own interactions. This is the basis of reinforcement learning. Consider how a squirrel navigates a tree. It doesn't study a manual. It moves, fails, and adjusts its approach until it reaches the reward. In this loop, the agent first perceives its current state within an environment. It then takes an action to move toward a specific objective. Every action triggers a consequence from the environment, either a reward for progress or a penalty for failure. This provides the agent with absolute ground truth, independent of human feedback. When the agent encounters a surprise or a failure, it updates its transition model, revising its internal understanding of how the environment functions. A reinforcement learning agent modifies its behavior based on the physics of its environment. Success is measured by achieving the goal, rather than by sounding correct to a human observer. Imitation learning relies on a finite resource. There are only so many websites and books in existence, and once an algorithm has processed them, it has no further source of information. Experience offers a different scale. An autonomous agent can run millions of unique simulations, generating its own data through trials that no human has ever performed or recorded. This principle was demonstrated when AI systems mastered the board game Go. Rather than studying human matches, the most advanced versions trained through millions of rounds of self-play, bypassing thousands of years of human strategy. By testing maneuvers and adjusting for the reward of a win, these agents develop strategies that human experts had never considered. As AI moves into physical robotics, it faces a world where every situation is a unique edge case. Success in the real world requires the ability to learn continually and adapt on the fly to new sensations. True artificial intelligence requires an agent to step into the world, act, and refine its understanding through the resulting consequences.